What's up, guys? It's me again, Chemical Engineering Guy. We're going to continue with section 2 of the mass balance course. We are right now seeing single phase, and we already see section 1. Hopefully you've seen it before. If not, go back. I think it's the video before, and yeah, the previous video. And yes, right now we're going to talk about gases. We've seen liquids and solids. These are easy to account for mass balance, but right now we're going to see gases. We're going to split them in ideal gases and real gases. Ideal gases are essentially gases that we can model easily. We'll see their application, standard conditions, the constant and some values, and some exercise and theory, of course. Finally, we're going to see mixtures of gases, and we will see what is partial pressure and why do we need it. Now, we're going to see also real gases that essentially are either equations. We're going to see a little bit equations, and we're going to see this decompressibility factor, which is very, very important. And we're going to see also this little theorem here. I'm going to explain it right now. And yes, this type of properties, reduce temperature, pressure, etc. And finally, K rule. So, yeah, gases. Gases, the problem of gases, rather than liquid and solids, are that they are affected by pressure and temperature changes. So if you change pressure, you've probably seen it before. You have a bottle and you, I don't know, like push it, you will compress the air and it will have another volume just because you added pressure. Or for the other side, you have a balloon. Hopefully you've seen it before, and then at night it's kind of like this because it's cold, and then in the morning or in the afternoon next day you will have it again like this because temperature, you increase it, you increase the pressure or volume, whatever you want to check. And yeah, so we cannot just say I have a volumetric flow of this gas. And actually the problem is that we will be saying that. So whenever we say that, we need to specify pressure and temperature because volumetric flow is not that convenient to work to. We will go with this data and we will transform this to moles, and you know that moles we can change it to mass flow. So we're not that lost, we just need pressure and temperature. And of course an equation that relates that variables, which is called an equation of state. It relates pressure, volume, temperature, moles, essentially. Of course, we're going to see gases that need a little bit more, like eccentric factors and some constant, crazy constant for polar or non-polar substances. But the simplest one we're going to be analyzing right now is the ideal gas law. And I told you before, they are more complex, of course they are more precise, but right now we're going to have this scope right now in ideal gas law. The good thing about this is we can relate pressure, temperature and volume to moles, and as I told you before, we can change that to mass and we will be able to check a mass. So imagine I told you this place right here has a volumetric flow of this gas, I don't know which gas, they tell you is 10 cubic meters per hour. So essentially you want to know how much, for mass balance purposes, how much mass is there. So you will need to ask what's the temperature, what's the pressure, what's the composition, and you will be able to calculate eventually the mass being lost by this gas. And as you can see, it's a lot of gas. So if you don't account for this gas, you will have no right mass balance in this plant. So let's do the ideal gas. Simplest form to relate these four equations is this equation. Hopefully you've seen it before in chemistry, because if not, be worried because you should have seen that before. And yeah, P is for pressure, always absolute. I will talk about that later. We use normally pascals. V is for volume. cubic meters typically. Now, N here, it's for moles of a gas. Which gas? Whatever gas. It could actually be total gas, mole of A plus B. Of course, you need to account for that temperature, pressure, and volume. And it is typically mole, gram mole. And R here, you will be asking why is it not here? Because that is actually a constant. The experiments were always like this. And you know that when you have this correlation, you need to add a constant. So they added this constant, which is cool. And the constant is typically given in many units. It does not have to be cubic meters, nor pascals, nor moles, nor Kelvin. It could be, I don't know, ranking. It could be pound, mole. It could also be atmospheres. And could be cubic feet meters. I don't know. You could change a lot, and the number, of course, will change. And finally, but not least, and I think this one is very important, it's temperature, and it got to be absolute. U in Kelvin. If you use normal temperature, I don't care if it's Fahrenheit or Celsius, it will be wrong. You cannot use normal temperature, it needs to be absolute temperature. The good thing here, it's good for low pressures and high temperatures. So we'll be analyzing those cases. Low pressures, I mean when atmosphere is relatively low. So most processes are at ambient pressure or atmospheric pressure. So it's okay. High temperatures, I also mean not below 0 degrees, like freezing. So if you're at 25 degrees, you're relatively okay. So I talked before about the constants are maybe calculated in any unit you can imagine. Joules, Kelvin, mole, liter, atmosphere, kilomole. And my favorite is here because it has the units of the international system. It's cubic meter, Pascal, Kelvin, mole. I will learn this by heart and probably these two, but actually you just need to learn one and change it with units. For example, you can change liter to cubic meter. Yes, you can. Actually, I think you just need to add this 1000 factor. And atmosphere to Pascal, yes, you can also. You just need to add this number here. Probably you know it. And yeah, you just need these two. And if you're using English units, I will recommend converting these to English units or learning any. Right here I don't have, but I think it's 6 point something feet square, and no, cubic feet. Use the PSI ranking, pound mole, something like that. Just find it. Anyways, you should at least know one because then you can change it. And if you don't know it, no worries, you can find these tables everywhere. Maybe your teacher will tell you that you need to learn it, but you don't actually need to learn it, but it's so recommendable. Now the limitations are high pressures. I mean like 30, like 300 atmosphere will be a lot. Of course it will not help. And low temperatures. And this is because at high pressures you start getting molecules more near. And they start collapsing and shock and I don't know, crashing everywhere. And they start not being a normal gas, but rather becoming kind of liquid because they're being compressed. And low temperatures, same logic. At low temperature, they start getting nearer, more near, and they start being kind of liquid style. So that's not good. So try to avoid low temperatures and high pressures. Now I've got this, it's like a thumb rule, how to know when to use the ideal or gas ideal equation. And I have this. For the atomic gases, remember, is N2, O2, H2, all those Hunkel-Brief guys, you can use this rule. If you get a higher density of this, you're okay. You're cool. You have 6 liters per mole, you're cool. You have 30 liters per mole, you're cool. And for the other side, with all the other gases, which will be probably a lot, you need to have at least 20 liters per mole, which is not that crazy, but I think you always need to check just in case to see. And as you can see, density is related with pressure and temperature. If you increase pressure, density drops. If you decrease temperature here, you decrease it, you will probably increase the density. So it makes sense with this. Hopefully you get it. If not, just learn it by heart and check the density at the end. So, yeah, as I told you, just review every time at the end. And why do we need to use this ideal gas law in mass balance? I told you before, sorry to repeat it again, but it's very important that you get that pressure and temperature will relate us to either volume flow or moles. And you know that if we have moles here, we can change it very easily if we know the composition to mass flow, which is the thing we need for mass balances. And we're going to see problems like this. Letter A, prepare a mixture of 120 Celsius at this pressure 2.3 bar with a flow of 250 liters per minute. So we have volume, we have temperature, and pressure. We could theoretically look for N. Now, 5 cubic meter of hydrogen gas is in a container. You have this temperature and you have this pressure. How many moles are inside? Nice. We have moles, we have mass also, because we know it's hydrogen. So now hopefully you're starting to get the idea why it's important to analyze gases. Finally, this is not that typical for mass balance, but imagine there's 10 kilograms of nitrogen, and you have this volume, and you have this maximum pressure. They will ask you to get the temperature. This is not typical for mass balance, this will be more like energy balance. But that's good because we're studying this in mass balance and you will be able to see it in energy balance and in many other courses like thermodynamics, plant engineering, many places. So that's cool. Let's do this exercise. 100 grams of nitrogen are stored in a container at 23 Celsius and 3 psi G. This G means gauge. Hopefully you know gauge is not absolute, it's just what your equipment just measured. So we're going to see how to treat this later. They ask you, or the question for you, ideal gas behavior, assume it, and calculate the volume. Verify this with good approximation. Okay. Anyways, let's do letter A. P if ideal. We have the equation. PV equals nRT. We just look for V, take out P down here, and then you have nRT divided by P. So, the good thing I told you before, I think, gauge. We need to add the total pressure of a system, and remember we need absolute pressure, is the atmospheric one plus the gauge one, because probably you've seen this tire, or I don't know. When you use this equipment and they tell you, oh, it's 32 psi G, it means that's the pressure in this air, the pressure of air inside this reel or tire. But we also have the pressure that we do not feel, which is the atmospheric pressure. So if you wanted to know the total pressure, please add all pressures, which will be atmospheric pressure plus the equipment pressure. We add this and we have the total pressure, it's 17. Now the same for the temperature, hopefully you know how to change to Kelvin. I will not get into that, just add this number. And we get the absolute temperature here. And finally we get the number of moles. We have mass, We don't need that much mass, we need moles. So we calculate for moles and it's 3.57 gram moles of nitrogen. And we have essentially everything. Just let me check the units. We have pascals. No, we actually have psi. We have Kelvin, yes. We have gram mole, yes. And we have cubic meter, yes. So I think I will change this pressure rather, because I know this one, rather than to look in the table and look for psi, because it will be a waste of time, I think, and I already know this, and I rather change this pressure to pascals than look for this special unit will be psi times cubic meter. I'm sure it will exist, but I don't know how much time I will take to find it. So let's change this number. It just divide by 14.7, and this will give me 1 atmosphere, or 101,325 pascals. Anyways, calculating this, I get this pressure, and yeah, I have everything right now. I have amount of moles, yes. I have R, yes. I just choose it. I have temperature, I calculated, and this one was the last calculation. So I have all the data. I do it, and I get this number, which is in cubic meter. I just multiply by 1000 to get how many liters I have there. So the container must be 72 liters. So they tell you again that if you could just make sure if it is a good approximation, let's do the approximation we've seen before for the error, remembering that we got to check the density. Checking the density, we have 72 liters per this 3.57 gram mole of nitrogen, and I get this. And since nitrogen is a diatomic, I just need to be over 5 liter per mole. And since I'm 20 liters per gram mole, I'm perfectly fine. So good. Let's do this example. We're going to talk about standard conditions, which include standard temperature and standard pressure. Standard values are typically values that are common in an industry. Actually, many industries and organizations have and use their own. The typical values I like and I think are common, it's 0 degrees Celsius and 25 degrees Celsius. For pressure are either 1 atmosphere or 10 to the power of 5 bars. But I have a table right here, and depends, I told you this before, this one is very typical. It has 1 atmosphere and 25 degrees. This is also typical, 25 degrees and almost 1 atmosphere. This is 10 to the 5 bars. And yeah, what else? Oh, UPEC, probably you've seen or heard of UPEC before. They have 0 and they have 10 to the 5 bars. And yeah, that's for the international system. You can also check for the American or English system. It is right here. They typically use 60, which is approx 15 degrees Celsius. And for the guys that have no idea what is 25 degrees, it's about 77 Fahrenheit. So I just know when I'm in USA, if the weather is about this, I am fine. If I'm near 100 Fahrenheit, I think it's hot. And if I'm below 60, it's cold. So that's the only thing I know. I need to change my calculations. If I don't know, if they tell me 700 Fahrenheit, I have no idea what is that. But anyways, let's continue. You can see I told you 60 is very typical, and they use PSI, and it's about 1 atmosphere, this atmosphere. This is almost the same as this 101. And they use USA Army, Metro, and OSHA, which I think is health or something like that, OPEC. And yeah, that's essentially some industries that use their own. Now, why do we see this? Because we're going to see, essentially, a lot of tips. Standard cubic meter per hour. What does this standard mean? Means that it is given at certain temperature and certain pressure. It will also help us to understand the amount of volume involved, because if I tell you I have 100 cubic meter of something per hour, it could be any temperature, any pressure, you have no tangible, or you cannot compare with nothing. And you have other gases and other temperature and pressures you will not be able to compare. So using standard cubic meters per hour, you will be able to compare easily. For example, you have 100 versus 125, you will know, of course, this is 25 more or 25% more than these. For the other side, if you didn't know the temperature and pressure, you cannot compare it. Actually, you could be having more matter here, more volume, because of pressure and temperature. Because we're going to reference these to the standard conditions, guys. So standard conditions, we're going to learn it a little bit later. I think next slide. And yeah, we can also use this data to simplify calculation, and we will see that also later. Now, as I was telling you before, if I tell you there's a flow at this temperature and this pressure, I have no idea if I tell you at this temperature or at this pressure. But if we use, or we get like to standard cubic meter per hour, will be, let's use a temperature and a pressure standard, so we can compare our flows. So let's do an exercise. Before that, I want to show you this, which is the standard condition. We're going to please learn it. You don't need to learn it, but of course you will need to check it, so I think it's better to learn it, and it will help when you do your calculations. This is a fact. 1 mole of any substance, it could be CO2, it could be O2, it could be, I don't know, chlorine, anything. Any substance at 1 atmosphere and 25 Celsius will occupy 22.4 liters of volume. So, to get an idea, I bring you this. All gases, helium, chlorine, will occupy 22.4 liters in this condition. So if you can learn that, you can learn P, V, T, and N. You know N it's 1. You know temperature is 25. You can change it to Kelvin if you want. Volume, 22.4 liters. And pressure, 1 atmosphere. You can learn this. I know it seems a lot, but actually it's easy. 1 atmosphere, come on guys, it's atmospheric pressure. 25 is like the coolest temperature ever in the weather. So you have that. And 1, come on, it's 1 mole. The only thing you need to learn here is 22.4, which is the random number. But once you learn it, calculations are gonna be easy. So, I told you before, we're going to compare about temperatures and pressures. So, imagine you have this pressure, this volume, 1, we have R and T. This is the same substance, so we're not going to, no, actually no, it's not the same. So N1 should be here and N2 should be here. Or NS, which will be 1. But anyways, we have standard pressure, standard volume, and standard temperature, and standard mole, which is 125 Celsius. Remember to change to Kelvin. Volume is 22.4 liters, and pressure is 1 atmosphere. And if you have no idea what this will be our gas. The actual gas, we have temperature, pressure, volume, etc. What happens if we divide 2 in 1? This will happen. R's or constant will go, and probably N, I don't know why, N will, if it's the same number, which it will probably be, you can take it out away. So you have the relationship. And that's good because we don't need R anymore. We get rid of R and you just need to learn pressure, which I told you it's easy, 1 atmosphere. This is the number I told you it's kind of tricky, 22.4, but if you learn it, you will avoid learning R. And the standard one here is 25. So good. Yeah, I was talking, yeah. Of course it, no, oops. It should be, I think this one should be 0. Yeah, it's 0. Yeah, make sure, let me make sure. I will make the correction in the video, but I think the temperature right here must be 0, which is also easy to learn. 0 degrees or 25, come on guys. It's like 0 is 0, come on, we have snow, or 25, it's cool. We have a pretty weather. So let's relate to ideal gases with their condition. So I told you before, this right here is one number, or one equation. This right here is another gas. They are different. P, T, B, P, T, B are different. Then what happens if we divide? We will get pressure here of 2, 1 down, 2 up, 1 down. And since R is a constant, we can get rid of R. And most importantly, what happens if the moles are the same? We can actually also take them out. So this equation right here is very important because we will be relating so easily volume and temperatures. Ooh, yeah. Yeah, I think it's, yep. So, let's do an exercise. Butane, okay, we can check the molecular weight. It's a temperature, yes, it's given, and a pressure, absolute. So it's good. It's flowing at this mass rate. So we could change this to moles. Nice. They ask us to calculate the volumetric flow rate of the stream using conversions with standard conditions. So you could either go and do all the large and RT values, or since we already learned everything, we can use this equation. And yes, because I'm not going to take out this N because N1 was 1 mole, but I don't have N1, I have this amount, which I don't know how much is, but I'm sure it's not 1 mole, so I cannot take this out. It's N I'm looking for, it's not the same as N1, which is 1, so I cannot take them out. I will take this equation as granted. First thing, standard volume, it's 22.4 cubic meters per kilomole. Or, don't get confused, 20 liters per mole, gram mole. So I will choose cubic meters and kilomole because I think it's easier. Now the standard, yeah, I was right. Standard one, it's 0, not 25, sorry guys. So let's use 0. And yeah, we could change it later to 73 Kelvin. The molecular weight, it's 58 kilograms per kilomole of B, of butane. And yeah, PS is 1. So what do we have, guys? We can check this, we have 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 the pressure it's given here, and we have the temperature which is given here. So we only need to find for this volume right here. So let's do it. Now, pressure is also already absolute. Okay, 360 Celsius will be this amount, remember. And the amount of moles will be simply the massive flow, which is this number, divided by the molecular weight here. And you get this number. Cool. We're getting data, and yeah, let's substitute all the data. This right here is the 0 Celsius, and this right here is the 360 Celsius. So we have 3 pressure. We know 1 atmosphere is PS. We know this guy here is PS. And what else? We have this here, N. We just find or look for this. So we send this multiplying and this dividing. We get the flow, which is 328 cubic meters per hour. Nice, we have the answer. And the good thing here is we did not use R, or the constant. So that's the advantage of using standard cubic meter per hour, or standard conditions, which is PS, TS, and PS. So you could either learn both. I will learn both because sometimes it's easier to do one and easier to do the other one. So yeah, it's up to you. Now let's do this little mass transfer, mass balance problem. 10 cubic feet of air, it's here. At 70 Fahrenheit, it's here. And 1 atmosphere, it's here. It's going to be heated up to 610. So this is the new temperature. And compressed to 2.5 atmosphere. The thing here is they don't tell you that actually compression generally involves temperature changes, but we're going to ignore that because this is just mass balance. This is not momentum transfer or heat exchange class. So let's suppose this is the actual value. What volume does the gas will occupy at this state? So we could either go directly and find the amount of moles here and then do PV equal nRT here, and we now know the number of moles, and we use this pressure here and we use this temperature here, and we need to look for the R that best suits. Or let's do this from the last equations, remembering that you could relate P1V1 with P2V2 equals T1T2. This is one state and this is the other state. We can divide them, and since it's the same amount of moles and R is a constant, you can cancel this. So it's so easy. We just need to substitute this pressure right here, which is 1, this volume right here, which is 10, and this temperature, which is 70 plus 460, because we're changing to ranking. We're using American units or English units. So, well, a mixture of it, because atmospheres, I don't know, I think they will use PSI. Now, P2, 2.5 atmospheres, and volume 2, we don't know it, so we're going to look for it. So take attention in this variable. And now temperature 2, which is the final temperature, 610 plus 460, is here. So actually you just need to check, do math, and you will get that 4 over V2 equals 1/2. And just go for V2 and you will find it's 8 cubic feet. Now, third exercise. The flow rate of methane stream, they give you temperature and pressure, and blah blah blah. They tell you that the flow rate is this amount, 3.95 times 10 to the 5th power standard cubic meters per hour. They tell you calculate the molar flow rate and the true volumetric flow. Okay, because this is a standard, this is actually not the real flow. We want the real flow, and we're going to see it later. But let's go first for the mass flow. So, the mass flow, the most interesting part of this is that you do not need the data here. This and this, because, no, I'm sorry. These guys and these guys, you don't need them, because you are given in standard conditions, and you know standard conditions mean 1 atmosphere and 0 Celsius, or 273 Kelvin. You know these occupy 22.4 cubic meters per mole. So let's do it. We know how many or how much volume per hour we have. We just need to divide or multiply by the amount of, actually divide by the specific volume, which is 22.4 cubic meter divided by kilomole. And as you can see, now this guy should not be here. This guy should be here. So you can take out cubic meter, and you get kilomole per hour, and you get this number. So pay attention, guys, we did not need this data here right now. When we do need it is to get the real value. So they tell you, please, PV11 divided by P2V2 equals N, no, actually just T1, no, T2, T1. So just look for V2 and you get this equation. And we have the first volume, yes, which is the standard one. And we have the temperature, the real temperature, yes, P1 and T1 are the standard ones, and T2, P2, and V2 is the real ones. So just substitute that. You know the volumetric flow, it's given in standard SCMH. And what else? We have also temperatures. Yes, we have the standard one and the real one here. And of course we have also the standard one and the real one. And yeah, it's all the things you need to do is just math. You have it here. This will be the real one, real. So this is, when I say real, I mean real, like how much volume will you need to get this? Because SCMH is just a reference number. It's not an actual value that you're going to use. It means that if you get that gas at that temperature and pressure, you will be having that volume. But since that is not the real volume, and that is not the real temperature, and that's not the real pressure, it's kind of tricky. It's just like a reference number, just to get to know if it's a lot or not that much, or to compare with other streams. But please make sure to understand that SCMH is not a real number. It's just a reference value. So yeah, I ask you again, why do we need temperature and pressure here? Because we need to make it real, and we need the temperature and pressure that the real gas, or that gas, is having right now. And yeah, finally we're going to see some mixtures, gas mixtures, because we know we generally have CO2, N2, CO, O2, etc. We have many gases. It's very common, so we need to count these combinations. So if there is A, B, and C, we have a Na, Nb, and Ac. And then we could use, I don't know, we add everything and we got the addition of total moles, and you could check for the molar fraction here. Or in case of a gas, use a partial pressure. What is that, you will be asking? Yeah, we're going to see that right now. Partial pressure is the pressure that the gas, let's say gas A, exerts to the real container. So imagine we have many here. Actually, we're going to see that later. Wait for it. So by definition, the partial pressure is the pressure exerted by the gas, which is the molar fraction here times the total pressure. So you have half of the container full of A. You will expect that half of the pressure is being exerted by A. So as you can see, it's directly dependent of mole fraction. If you have more YA, you will expect more pressure exerted by A. You have little YA, you will expect not that much pressure exerted by this gas. So let's say this. With the new definition, we can say this. PV equals nRT, this is ideal law. And the same, but right now we are going to use partial pressure of A and moles of A. I think it and volume of A, of course. But these one and these two, we're going to divide it. Dividing them, we have this equation over here, and we have this equation over here. So the volumes are the same, because you're in the same container. And R goes away, and temperature, because of course the gas is the same temperature, goes away. So you just get with this. And by definition, Na over Nt, as I told you before in this slide here before, Na divided by total moles will be Ya. So I'm just going to take out this P here, and you get used to this here. It's the same, exactly the same. So this is how I prove it. I think it's not that complicated, but if you need it, take it. And you will see also that fraction of A, fraction of B, plus fraction of C will give you 1. And pressure of A, partial pressure of B, and partial pressure of C will give you the total pressure. So I hope you understand a little bit. This is not that complicated. And yeah, let's keep going. So imagine we have A, B, and C, and we have partial pressure of A, partial pressure of B, and partial pressure of C. Each gas, if we combine them, to make a mixture, the total pressure that we will exert will be A, B, and C. Partial pressure, of course. It makes sense because they're occupying 1/3 of the space. They are 1/3 of the composition, so 1/3 of the pressure makes sense. Now, by conclusion, just so you understand, you have this equation. Partial pressure of A is here, mole fraction of A is here, and total pressure will be here. It could be either PT or just P. Also useful, the same equation but just changing numbers. How to know the mole fraction, or how to get the mole fraction from a partial pressure. And I think this one is very important for our mass balances. Why? Let me explain you why. Because many times they will tell you the partial pressure of A is, I don't know, 100 pascals. And they tell you the total pressure in the stream is 250 pascals. And you don't like that much to work with pressures. We want to work with moles or mass fractions, mole fractions. So we could use these here, use this equation and find the mole fraction. With the mole fraction we can do our mass balances way more easier. And yeah, I think we're done. If you need more exercises, I will be posting them here in this webpage. Here, just go to courses, then click mass balance course, and you will find a lot of problems here. I'm going to let this exercise for the next video. See you then. What's up guys, it's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos or if I should be changing something or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. Thank you guys for the support and the love.